So just so you know, everybody, we're recording today. I'm just kind of like we do online. What's that? No, I'm staying up. I mean, I'm without anybody being connected. I'm making a video just like I do when I do the online. But the voice is different. Why? Because I got a couple of people are going to be gone today, and I thought this might help. And then you guys connect the other one. So, yeah. I mean, at one point, I was even thinking of doing it every class, but right now, just today. Yeah, I don't know. The only problem is they're all quite long. So we'll see how. I'll do a one. Somehow I'll do it. I'll see what I'll do. Give me the problem. I'll work it out in detail.
Oh, that would be perfect.
I'll do it on video, and then I'll publish it.
Yeah, that's what we'll be.
Here's the problem. Those things will take a half hour.
Yeah, no, I understand.
At least. It was just where I thought it was. It was in a folder that was neatly tucked on my desk. Yes. So I'm getting through the struggle of getting these, the long story. Kind of my whole schedule, whole professional schedule is kind of based on doing things on the day they were due. And so whenever I have these things that are done at different times, it kind of drives me crazy. And by that I mean, just anyway, so I finally got to 2 tests from the, would you believe, from the last chapter that were taken late, and now they are corrected. And now I've still got to proceed. Someone wanted me to look at again, and that's my next test. So just so you know, they'll be waiting this weekend. So, I just had a question here. The question was, can we go through the problem from this last time? I'll always be happy to do that. The trouble is, they're quite lengthy. So I think what I'm going to do is, Damon, which one did you have an interest in? I'm sorry.
19.
I'll take other requests. I don't know how many I can do, but I'm probably going to work them out on video and send them to you. And the reason is I just can't afford a full half hour per problem now. So I'll take that approach, and then we'll see if we need to follow up on it. Are there any, I realize this is related to the problems, but are there any from the previous? This was where we put all the tools together. Let me put it this way, were there some tools that you had kind of got a little foggy in your mind and a little bit hard in the back? Yeah, that's one of the problems with many tools. Yeah, that's natural. Any in particular you want me to talk about? Tools? Here's one I got a feeling it was way past. You remember how to use the symmetry test? Why is symmetry a big deal when you're graphing a strange function? Well, if you find out you've got left-right symmetry, for example, all you have to do is figure out half the graph. And you can copy it. So it could save you half the work, or maybe even more. So it actually is a big deal. Here's the symmetry test. So let's assume you've got f of x equals such and such x. Okay? Well, let's see if somebody else remembers. What do you do to check for, let's say, x-axis symmetry? Like, for example, let's take one we know, y equals x squared. Everybody knows this parabola that sits right on the origin, and it's beautifully symmetric about the y-axis, correct? How could we, if we didn't know that, how could we take y equals x squared equation and find out that it's symmetrical? The way I always taught my students was plug in a value for x, something other than 0, like 1. What's the answer when you plug in 1? 1 squared? 1. Okay, now take the same number, only with the opposite sign, -1, and plug it in. Okay? Do you get the same answer we got before? Yes, we got a 1 both times. That's a candidate for y-axis symmetry. Why do I say only a candidate? Because you got to check more than 1 point. You should probably check 3. So let's plug in 2. 2 squared is 4. All right, let's try -2. -2 squared is 4. Yep, so far it worked both times. Does it work with 3 and -3? Of course. So what does that tell us? Y equals x squared is symmetric about the y-axis. Okay. So now, what happens when you plug in, let's take x cubed. When you plug in 1, you get 1. When you plug in -1, what do you get? The same number, but with the opposite sign. Is that happening? Try 2. 2 cubed is 8. -2 cubed -8, yeah. So now what does that tell you symmetrically? That's called origin symmetry. So in other words, everything up here is mirrored on the opposite side of the origin. Everything, you know what I mean? X cubed, you guys all know what that looks like. Gotta do it backwards. And you know that everything over here matches up on the opposite side of the origin. So anyway, that's not the whole symmetry test, but probably a good thing you had to refresh a couple, you want to refresh a couple of these tools because they really are powerful. Okay, so we have a 2-day so I promise you, I don't know if I'll do both of these, but I'm going to look at those. Maybe I can do both. And I'm gonna have, I don't know when they'll be ready, but I'll basically teach them to myself. I'll take a video of them. And then, yeah, and if I can't learn from myself, then doggone it, you guys can't either. No. Anyway, probably true. But anyway, I'll send you the videos, see if that does it. If it doesn't, we can talk about it some more. So what we've got is a 2-day lesson. Now I gotta tell you, you see the title? It's like the optimal calculus day of the semester. And that's not just what? A pun, because we're going to be talking about optimization. But it's like, this is really why you want to learn calculus. And so this is kind of, I'll be honest, I've been anticipating this for quite a while. Let me give, here's the classic example. This is not the problem, but the classic example in calc is this. If I gave you guys a piece of cardboard that was a rectangle, and it had given dimensions, and you could, let's say, take the rectangle. So let's just say it looked like that. You could, cut some slits. I'm gonna put this out like. You want to make this into a box, okay? So if you have scissors, you can cut out the corners, cut these pieces away. Okay. I got it. Just hang on a minute. No. Yeah, we cut those out. And then you could fold up the sides. And you would have a box. Got it? So like you cut these out and then folded those up, folded those up. Can you see that you would have a 3D box? So the classic calculus problem goes like this. If I give you the dimensions of the cardboard that I give you, what size square would you cut out to make the volume of the box the biggest? Well, how would you go about that? I mean, how would you go about that problem? We could do what? 1 trillion experiments? Make all these boxes and we could calculate all the volumes? I can show you how to do it directly. Calculus. And it's the first derivative that does the whole. So here's the deal. What we're going to do, and that'll be our first example today. We got to find the volume formula for that box, because finally, isn't volume what describes how much the box holds? So what we're going to do is find a volume formula, and then guess what we're going to optimize it by? Well, you tell me, how do we find, let's say, the top of a curve? How do I find that high point? Using calculus. You're really close. You said find the second derivative and set it equal to 0. If you set the second derivative equal to 0, that'll give you the point of inflection. Is that what we're looking for? It's a yeah. And if the first derivative is equal to 0, that tells me we got a horizontal tangent, which means we're going to be on the top of that arc. Exactly. And that's exactly how we approach this problem. Find the volume, take the first derivative, and set it equal to 0. And that'll tell us. So do that. See, I didn't get my pen out. Okay, I got all kinds of things going on here. There we go. Okay, here's the setup of the problem. So here's your piece of cardboard. And now I'm going to tell you it's 24 inches by 24 inches. So it's a square piece of cardboard I'm giving all of you, okay? 24 by 24. And we're gonna figure out these corners like I was trying to show you up there. Okay, so I wish this wasn't labeled, but yeah, I guess I'm just gonna redraw it. In fact, I'm just gonna get this out of here. All right, so we've got ourselves this rectangle. And it's 24 by 24. And we already know that what we're going to do is this. We're going to do this removal of corner type of thing. And the question is, how big should we make those corners? So what I'm going to do is we're going to call this dimension, you know, that little square I'm going to cut out in the corner is, let's call it X inches by X inches. And of course, that's the key. What is X? So, what we will get is a square, a box that has a bottom that's U-shaped, correct? And then what will the height of the box be? After I fold the sides up, it'll be X, right? And what are the dimensions of them? This dimension right here, down here. Well, it was 24. Right, because we cut 2 X's. I'm sorry, again, sloppy. Let's try that again. Does everybody see this is 24 minus 2X? Because it was 24 and we just cut an X off of each end. And won't this be the same thing? This other dimension, 20 minus 2X also. So I've got a square on the bottom, 24 minus 2X by 24 minus 2X. Okay, now, what's the volume of a rectangular solid? Length times width times height. What's the length? 24 minus 2X. What's the width? 24 minus 2X. What's the height? Can all of you see that'll be X when you fold up the sides? So there's my volume formula. Does that make sense? All right. I guess we better hammer that sweetheart out. So 24 times 24. Wow, what is that? 576? Yep. Okay. 576 minus 48x minus another 48x plus 4x squared. And that still all has to be multiplied by x. So I was just multiplying out those first 2 parentheses. Simplifying, what do we have? I'll put it in different order. 4x squared minus 96x plus 576 all times x. So finally, let's multiply out the x. 4x cubed
minus 96x squared plus 576x. Does that look correct? So the whole volume is based on how big of an X cut we make. All based on X. So now, let's use ideas that James had over here. Let's find the derivative and set it equal to 0. Okay, so what's v prime? Easy derivative, right? Power rule. 12x squared minus 192x plus 576. Let's see, 96 and 96, 180. Yep, that's correct. All right, now set that equal to 0. All right. Wow. So now it's algebra time. How do we solve a quadratic set equal to 0? Well, we have at least 3 choices. We could try factoring. We could do completing the square. We could use the quadratic. Huge numbers for the, okay. So is there anything, first of all, can we cut these numbers down at all? Since it's equal to 0, couldn't we, what, divide through by some, yes, go ahead. 12 goes in all of them, thank you. So 0 equals x squared, and what is that, 12 times 8? No. 12 times 16 is 192. Okay, 12 times 4 is 48. 96, we're up to what? Yeah, 40. Okay, well, that looks a lot better. That's factorable, isn't it? What 2 numbers play out to 48 and add up to negative 16? How about 12 times 4? Negative 12 times negative 4. That'll work. You guys agree? Because in the middle you get, I mean, 12 times 4 is 48, and negative times a negative is 2. Negative 12x plus a negative 4x is a negative 16x. Do you see that we have it? Okay. So now, what's the solution? There's 2 of them. Okay, now, take a look at those 2 answers. Take the first answer, 12. Remember, this thing was 24. So what if I cut off 12 inches? The bottom is gone. Yes? 12, 12. We don't have a bottom anymore. The volume is not going to be too good if you have no bottom. Okay, so even though that answer came out legit, we're going to reject that one. How about 4? That should be your guy. And if we just, let's just, what is the volume at 4? By the way, all we got to do is go back up here and substitute it in, right? 4 times 2 is 8. 24 minus 8 is 16. So 16 times 16 is what? You should know this. $256. So 256 times 4. 1024. You can't do any better than that. I'm telling you right here now, that is the best anyone will ever do. They can experiment on this for hundreds of years.
size to make that, to get the biggest volume. You know, you can just think, if I make that smaller, that'll make the bottom bigger, right? You cut out smaller amounts to make the bottom, but what else is it? It makes the height smaller. So it's like give and take. And this is telling you, this is the epitome right here. This is the best. This is the top of that curve. By the way, can you tell, anyway, I guess I got off track there a little bit. So this is a classic example of how you can take a pretty mundane problem. I mean, this is high school volume, grade school maybe. And now we're talking about really cool things like where's the best place to make such and such happen. And without calculus, well, you could get close. Somebody over here could say, well, I got up to 1,000 cubic inches. And then over here, oh yeah, we got 10, 16. And you could play, you could maybe have a fun contest, but I'll tell you right now, that's the best. Of course, we could also set it up so that the answer would be 3.735. And, you know, it might not be easy to guess and try. Calculus lets you go right to it. So does that problem make sense? That's kind of a classic optimization kickoff to get us going on this. All right, let's take a look at some of the problems in the book that they're not all related to geometry like that. Here's the first, first 8 exercises. And I'm just checking in my book so that I'm going to avoid doing the ones you have assigned to you. Okay, let's take number 4 as our first example, or example, I should say. The product, and let me circle here. We could do any of these. Okay, number 4, the product. So it says find 2 positive numbers that satisfy the given requirement. So we're looking for 2 numbers. Okay. And in number 4, it says here's the 2 characteristics you have to have. Their product, when you multiply them, is 185. And when you add them up, you'll get the smallest possible answer, minimum. So here's our first minimum problem. All right. Well, I suppose you could say what? We could say the 2 numbers are, except I should do it the other way. Let's say the 2 numbers are x and y. By the way, we're not going to want to stick with 2 variable law, but we do know this. Their product is 185. Okay, now we got to get to the sum part, but before we do, I want to name both of these in terms of x. So what would happen if I solved that equation for y? Right? So there's an alternate name for y. So now what are my 2 numbers? So you see how we have it all in one variable now? All right, cool. Now comes the sum part. Their sum is a minimum. So their sum, I'm going to say f of x equals their sum, x plus 185 over x. So all I did was add them up. Well, we need to simplify that, right? So let's get a common denominator and proceed from there. So obviously what? This fraction here, we got to multiply by x over x. And then that'll do it, won't it? So what do we have now? You know, maybe I should have left it. Let's leave it in the original form. My apologies. There's nothing wrong with what I did, but you know what? Let's just rewrite this as f of x
equals x plus 185 x to the negative 1 power. So all I'm doing is changing the format a little bit so that you get what I'm getting it set up for. What did we do before to actually maximize or minimize this thing, optimize it? It's the Witkowski technique, which is take the derivative and set it equal to 0. So f prime of x equals 1. And then it's going to be plus a negative, so I'm going to say minus, bring the 1 down, negative 185 times x to the negative 2 power. Okay, so now let's translate that back into another form of algebra, minus 185 over x squared. Okay, when will that equal 0? Well, we could add 185 over x squared to both sides. Couldn't we now multiply both sides by x squared? And then all we got to do is take the square root, right? So what do we got? 185. Where is square root? There we go. So x, I'll just write it this way. X equals plus or minus square root 185. And what was the number again? I got it here. Yeah, it's about 13.6. Now, all we did was find x. The book says find both numbers. So now that we know one number is 13.6, how are we going to find the other number? Just remember the original problem was the two numbers multiply out to 185, right? So don't we have to just divide 185 by this? Now, I mean, so we found, I guess let's do it real quick. What is 185 divided by 13? Let's do this way. Let's bring this back. Okay, 185 square root, and I'm going to store that answer and then do 185 divided by memory recall. Yeah, the two numbers are the same.
We know that just because it's 13.
Yeah, I would have known it in the last step.
Yep. Okay, so in this case, not that complicated. It turned out to be a square root. Sometimes they can get a little bit messier, but so the two numbers are, and by the way, what if it's a negative? There's actually two pairs that work. There's plus 13.6 and plus 13.6, and there's minus, that's one pair, and the other pair is minus 13.6 and minus 13.6. Did they say they were positive? Oh, they did. So we're going to scrap the negatives. Do you see that in the directions? Find two positive numbers. So even though there's a negative set, they told us only to find the positive one. So you got to always check back with the directions. Yep. I would say square root of 185, comma, square root of 185. Those are your two numbers. You want to list it twice because you remember you're finding two numbers here. Okay, so I wouldn't put the plus minus down because of the directions on that one. Okay, let's go back. If I can find the original. Let's make a new slide here. All right, let's do number 6. Did anybody have a question about number 2? So again, find two positive numbers that this time what? The second number is a reciprocal of the first number and the sum is a minimum. The second number is a reciprocal of the first number. So if I just start off and say, all right, my two numbers are x and y. The second is the reciprocal of the first number. So now, what are my two numbers again? Only this time, only give them to me in x. Right? And now from here on in, this is almost exactly like number 4, isn't it? It says the sum of the two numbers is a minimum. So now you're going to say f of x equals x plus 1 over x. And we're going to go through the same process. Find the derivative, set it equal to 0. I guess let's do it. Okay? So this time, right away, I'm going to rewrite this as x plus x to the negative 1 power. And so what's a derivative? Josh? Okay. Which is 1 over 1 minus 1 over x squared. So I'm agreeing with you. You're right. Okay. There's the derivative. Set it equal to 0. Add 1 over x squared to both sides. What's the answer? One. And what's its reciprocal? 1. And when you add them, the minimum sum is 2. They're saying you're not going to do any better. So for example, what if we took 2? Let's just try 2. What's the reciprocal of 2? 1/2. What's 1 plus 1/2? 1.5. See how it's bigger than 1? It's, whoops, what did I just do? Yeah, it's bigger. It's 1.5. Okay, we did some. I did some. The second number is a reciprocal of the first number, and the sum is a minimum. So 1 plus 1 is 2, and the other one was 2 plus 1/2, which is 2.5. Thank you. If you take 7 plus 1/7, it's obviously bigger than 2. So you'll. I mean, I'm just trying to demonstrate to you that it really works. Okay, now let's do number 7, which throws another twist in there. So let me copy this again. The sum of the first number and twice the second number is 108. Product this time is a maximum. Okay, so already we got something a little different. So let's say the first two numbers are x and y again. Just you know that eventually we don't want 2 letters, but 2 numbers, x and y. The sum of the first and twice the second is 108. So you can certainly see that we could solve this little linear equation for y and get an alternate name, right? So 2y equals negative x plus 108. Both sides by 2. Y equals negative 1/2 x plus 54. Right? You know you got to divide both things by 2. So now what are our two numbers? X and a little bit more obnoxious, -1/2 plus 54. And now their product is a maximum. Okay, their product is a maximum. Well, let's just make it into a function. So first of all, there's the product. Okay, let's multiply that out. And now that almost ever-present technique for optimizing, time for the derivative. You know, you can just almost see this guy in this skin-tight suit with a big D on his chest. Derivative man comes running in. Sorry. Too early. Find the derivative. I knew I should have dressed up this morning. Okay, so anyway, when you take the derivative, what do you get? 2 times -1/2 is -1x, and then plus 54. Set that equal to 0. Okay, so we got one number, 54. What's the other one? You have to take that number times -1/2, which would be negative what, 27? And -27 plus 54 would be? Yeah, positive 27. So they don't always come out to be identical, like those first two examples I think we did. So here, and of course the key is the fact that they had this in there, the second number, twice the second number. That's what caused that to happen. Okay, any questions on that one? Yes. That's correct. Why is that? Because we found x is 1, and what's 1 over 1? So maybe I should have done that up here too. On number 8 or 6, whichever one we were just doing. On 7, I should have come back here and we found x was 54. And then when we found the other one, we got 27. Yeah, the two numbers. Okay, we got another variation in number 8, so I'd like to go look at that one next. Copy, new page. Okay, number 8. The sum of the first number squared and the second number is 54, and the product is a max. Two numbers, x and y. The sum of the first number and of the first number squared and the second number is 54. Okay, we don't want a y, so we're going to solve for y. So now we've got an x name for our, so our two numbers are now x and 54 minus x squared. Okay, so now set up the function. And what does it say? Their product is a maximum. So f of x equals x times 54 minus x squared. Of course, we can multiply that out. And now derivative man comes streaking onto the pavement and he says, all right, I'll do my thing. Stop chuckling because the guy is wearing red skin tight underwear, okay? Anyway. I did say streaking, didn't I? This is true. That didn't help, did it? My apology. Okay, easy derivative, set derivative equal to 0. Solve. Divide both sides by 3. And what is that, 18? Right? Yeah. And then, of course, we have square root. Now, and by the way, again, these are positive numbers, so I'm not going to do the negative square. Normally, a good algebra student says I got to take both roots. But remember, you remember the directions way on the top? Find two positive numbers that. So because of that, now you guys we should be able to simplify that. That's what, 9 times 2? So there's x. 3 times the square root of 2. So now we've got this one. So now we got to find, if that's x, what's 54 minus x squared? Well, remember, 3 times the square root of 2 is actually the square. That's really 18. And what happens when you square the square root of 18? You get 18. And what's 54 minus 18? 36. So for my answer, I would list those numbers then. 3 times the square root of 2 and 36. Yep. Right here? Okay, that was the word of the problem where the product is the maximum. So what does that mean? Product, multiply. So all I did was take these two values right here that we figured out and I multiplied them. Yeah. So it comes from the words of the way the problem is set up. Okay, so there's the first bunch. Let's take just a peek second. And we might be able to do one of these. Let's take a look at number 10. Now, instead of all of them starting with numbers, you notice less exact. It says the perimeter is P. There's no number there. So it says find the length and width of a rectangle that has a perimeter of P and a maximum area. Okay. So how does one, so the perimeter is P. How does one find the perimeter of a rectangle? In terms of length and width. Yeah, 2 lengths plus 2 widths. Okay. Now, so right, I mean, the P, we're going to kind of just, and we're really working with 2 variables here, L and W, but we don't want 2, we want 1. So I got to think, how can we do this? We actually have 3 letters here, don't we? Well, I'll tell you what, let's just do this.
Well, we know that the maximum area for the rectangle has to be square.
Okay, well, that's cheating, but that's true. That's true. Right now, you're going to get some in a little while that you won't be able to do that on, but you are correct. I'm going to say it this way. Let's just call that the function, okay? And I got to think about this. You know what? Let's do the number 9 first. 80 equals 2 lengths plus 2 widths. So 9 is the same thing, except they gave you a number. And so we don't want L and W, so let's solve for W. So 2W equals 80 minus 2 lengths, and W equals 40 minus L. So our two numbers are now L and 40 minus L. Now you could go ahead and multiply them, because to find the area of a square, you have to multiply the two. And now you could maximize that. You're right, it's going to come out to be a square, but let's just do it. So this is 40L minus L squared equals f of x. F prime of x equals L minus 2L. Set it equal to 0. L equals 2L. Divide both sides by, what's that? Yeah, that's a pretty bad derivative. Thank you. The derivative of 40L is 40. So, not surprisingly, the length is 20, the width is 20, and that's a square. And if you take 20 4 times, you really do get the perimeter of 80. So I'll come back and I'll do number 9 next time. We're kind of out of time. But I do want you to look at the assignment. So this will be continued. But look toward the assignment, which is 3, 5, 9, 11, 20, 23, 3, 41, 47. It's not that terrible of a list. What is that? 9 problems? You can start on that, but we will another day through some more complex ones. Okay, thank you.